remember to like rotate it and whatnot so that things are visible.
Okay, so thanks guys for coming. Today I want to discuss manifolds and tangent spaces.
Wait, sorry, quick question. Who doesn't remember his name? Okay, exactly. Say your name. I can cut it out in the video, but
No, it's fine.
just say your name because I don't think everyone knows you.
My name is Sasha. And I will tell you about manifolds and tangent spaces. That's important, not my name. So essentially, as it was mentioned either a week or two before today, is that when we come to like a random blob in a multidimensional space and we want to talk about directions on it, or like somehow like define motion in it, for example, we have a fundamental problem, is that like direction is not well defined. And today's definitions and approach is a very legit way to fix that issue. So let's try to build up some formalism. So we will start with something boring but necessary, is defining like it. All that I'm going to discuss is happening in something called Hausdorff space, which is basically a space where you have, wait, where is the colored chalk? So like where you have two distinct points. I can always always draw two intervals around them, like that contain them, that will be disjoint. This is kind of the definition of the space we're working in. I mean, whatever, right?
So one thing I'd like to comment is that once I have my space and I put coordinates on it, and those coordinates are nice enough, then you kind of get all of these Hausdorff properties automatically. Like, so it's if I can put coordinates, it will be Hausdorff.
So pretty much, as far as I'm concerned, we need this property to already have some system of coordinates at the space where we have this blob, where we have our, what we will later call a manifold. So
I'd say if it's a Hausdorff space, you're not guaranteed to have coordinates. But if it's not Hausdorff, then you can't put coordinates on it. That's for sure.
Okay, I'm not sure if it's a word, but if one set is homeomorphic to another, that means that there is a continuous map from one set to another. AB, a continuous bijective map, phi, with another enforced condition is that the inverse is also continuous. Okay, also kind of makes sense. And like boring but necessary thing. So if we let a Hausdorff space and we take a region, and in that region we specify a point, and around that point we specify a neighborhood, and it will turn out that this neighborhood around this point is somehow homeomorphic to some set in Rn. I mean Rm. It doesn't. Okay, let's just kind of like agree on convention here. The big manifold will be in Rn, and every other sets I will discuss, unless stated otherwise, I will mean Rm. Like it doesn't have to be the same dimension, but it can be if you want to. So if this neighborhood can be is homeomorphic to some open set in Rm, for simplicity, I will also draw circles, because that's the only thing I kind of know how to draw. And we have this map phi. Then this is what we call a manifold at a point P. Like this thing is a manifold at a point P if we have this satisfied. I'm not sure, should I like write it down or no?
Sorry, a manifold at a point P was that a definition in the?
Yeah, in the
That's a silly definition. Okay. So at some point, I think you should keep going and then write down the definition of a manifold in general once you get to it. That you should write down and do a recap, but I think for now, just keep going. This is like a general exposition.
Okay, I think it should be clear, but what does it mean to have a continuous function between sets? Like how do I know if a function is continuous? I can give you two sets, how do you define a function to be continuous? I think this is very important when defining manifold.
Well,
a manifold is not just anything, it's a topological example. So what does continuous mean?
I mean, hopefully, that's my best guess. The fact that you enforce this space allows you to define.
So not exactly. Like.
Okay, then I have no idea. I'm sorry. I tried.
Okay. So the setup here, that I'll kind of go a little bit before what you're saying. Before you actually say it. The setup here is I have some set. And on the set, I have a topology. Don't really worry about what that means. But that just means that I know which subsets are open sets. That's it. So like which subsets are kind of like an open interval. Okay? And the goal of what a manifold is, if I have a sufficiently nice topological space, then maybe I can put coordinates on this space. Meaning that I can somehow parameterize the space by saying that this point corresponds to like this n tuple of numbers, right? So for example, you probably talked about this, but for example, a sphere, right? Locally, I can give it some coordinates. Do you agree? And I can talk about, say, polar coordinates or something to specify points on the sphere with just numbers. Do you agree? And so that's essentially what we're going to try and develop today. Is if I can put coordinates on some space, how can we kind of develop some notation for that? And also, if I can put some coordinates on that space, then in some sense, I should be able to talk about directions. If I'm at a point, like I should be able to talk about directions. And okay, that's going to be kind of the second thing. But the idea is like, we're going to look at how to put coordinates on something. And okay, I think the easiest way to think about it is, so to answer your question, is suppose I have some arbitrary set with absolutely no topology on it. And if I could put coordinates on it, then I can use those coordinates to define a topology and then not worry about it.
The reason I'm asking is when we'll talk about final models, I'll keep on looking at pre-individual stuff. And for that reason, I think I don't think we should, I think we need to define the topological spaces. I can like, if you're not familiar with the definition.
I think you should keep this in you can introduce this in our discussion of fiber buttons. Separately, just because this is set up already in a slightly different way, so that you break up the flow.
Okay.
But I kind of agree.
Wait, what happened?
What happened was you used this word open set, and we haven't said this. You're saying that you have an open set around around the point P, and we haven't quite said how would we know what an open set is there. But the point is, suppose you knew what the open sets are on that kind of space. But okay, just keep going and things will become more clear.
Just one thing. I don't care. What open sets are is not that important, but what continuous functions are defined are important depending on open sets. So maybe
yeah. We'll discuss that, I think, in your presentation.
Okay.
He will say there will be continuous functions between charts that coincide.
Oh, okay, but we know what a continuous function on Rn is.
Okay, but
and that's kind of what I said, that like the whole actions happen in like some like Euclidean space, and a manifold, like we just like want to reduce it to the manifold, well, not the space, but like we want like localize the coordinate, or well, what? Okay, whatever. So yeah, and the way the textbook continues is that if a set is a manifold at every point of it, then it's just calls it a manifold without specifying the point. Do you have to object? Like something to object?
No, I think that's right. But now you should write this down. You should
Okay.
write down overall what the definition of a manifold is, maybe where there's more space.
So let Hausdorff space no, Rn if
So you don't need this discussion of Hausdorffness. You don't need this discussion of Hausdorffness at all.
That's how textbook proceeds.
No,
okay, shall I
erase that? Erase that. No, erase it
like completely? Okay.
Yes, using a thing. And so okay, just say.
Okay.
Let you define a manifold and say let M be a subset.
M Rn.
Not necessarily a subset of Rn, just any set.
Okay.
M be any set.
Sure.
Okay.
Set M.
Okay, and then
if neighborhood. Oh, actually, well, yeah. If U.
This doesn't quite work.
No.
Sorry, let me think about it. Like I was hoping that you would give the definition in terms of at every point I have some set around it, which is homeomorphic to a set in Rn.
Oh, okay.
And then the transition maps are
so for all P in M, neighborhoods around P.
There exists a neighborhood.
Yeah.
With a
such that UP is homeomorphic to some open subset of Rm. This is the definition of m-dimensional manifold. Yeah. It is, right?
Not quite.
No?
Because, so this is kind of the point that she was making, that okay, if you say homeomorphic, then you need to have a sense of in what sense your map is continuous going from M to Rm. And that's why I was suggesting when we met that to avoid having to talk about this, you should instead give the definition of a manifold in the following. That I have some collection of UIs equipped with UIs phi i's, where for every point of the manifold it lies in some UI, and that the phi I is a bijective map between U and some open set of Rn, and that the transition maps are continuous.
Mm-hmm.
So okay, try and write that down, and then we will discuss.
Okay.
So write it on the second board. And we'll draw some pictures. So just erase that, and we'll start on the second board.
Okay. So here.
Yeah. So okay, let M be a set.
Sure. Let M be a set. For every point P.
So no, stop.
No?
Erase this, and then say, suppose I have a collection of pairs UI, phi I. U is capital. ui comma phi I. And put something like, yeah, exactly. And so this phi I is a map, phi I being a map from ui. Don't write is, just do like the notation for phi I colon ui arrow.
Phi I
Is a map from ui to rm. No, just.
Okay,
Do you see
okay.
what I mean?
Like this way?
Yes, okay, correct. To rm. Okay. And sorry, yes, phi and phi. Oh, actually, sorry. Let's phrase it in a more confusing way. Phi is a map from ui into phi I of ui subset of rm. Let's do it like that.
Okay.
So it's like phi I is a map to R is a map to the image of what it maps to, which is a subset of RM. Subset, not element.
Okay.
Subset, not element of subset.
Oh yeah, sorry. Okay. With this, what should be?
Oh yes. There's a random vertical line.
Does it matter?
It doesn't matter. It just doesn't need to be there. But that's okay.
Okay.
So
this means restriction. That's why.
oh
Is it?
yes, that's true. Yes. So
Okay.
doesn't matter.
Okay.
That's already like we're getting nitpicky. Okay. So you have, suppose I have my manifold, and then I have this collection of sets and maps, which map UI into something in RM, and I want these phi i's to be bijective. So demand that phi i's are bijective. Write this down. Where phi i's are bijective.
Okay, with this convoluted definition, the first half of my prepared material breaks down.
Yeah, that's
just for the context. So
I just failed to communicate that this is what I wanted. This is the approach I wanted you to take. So that's okay. So where phi I is a bijection. Okay. And now, what are the conditions you want? So let's draw a picture of this. So grab some other colored chalk. And what do we, question to the class, not even to you. So I said at the beginning that I want to kind of have some set and then put coordinates on it. So based on what has been said so far, how is this going to give us coordinates? Based on what has been said so far. Yes, so Rm is like the coordinates that we're going to use. And this phi I is going to be this map that's going to do what? It's going to assign two coordinates. It's going to assign someone else.
I'm sorry, it's going to assign two. Oh,
So
assign something to coordinates.
Yes, assign what? A point in UI. Yes, in UI. So hopefully what I'm going to do, I have a bunch of these UIs which are subsets, and these sets somehow look exactly the same as some like patch in RM. RM has, that literally is coordinates. That's what RM is. It's like sequences of numbers of length m. That is exactly what coordinates are. Do you agree? So what I will do is I will take a set in P, and then I will use these phi i's to give it coordinates. Okay. And then hopefully I can then use these UIs to cover all of M. Okay. So this is exactly the picture, but the picture here is slightly reversed because you want that's psi I or phi I. Because your phi i's here are going from UI to.
No, that's psi.
Okay, so if that's phi, so there you wrote down phi going from the manifold into the coordinates. Maybe you want to switch.
Oh, yeah, okay.
Okay, you can pick to switch whichever one. It doesn't matter because they're bijective.
Yes.
Actually, maybe I would rather have you switch the.
Like that is better.
I would
no?
keep that and then switch the definition from kind of.
Okay.
Well, actually, it would look ugly. I don't know. It would look ugly. I think.
That I mean, it looks ugly anyways.
So maybe, because then it would be like phi inverse of UI. It would have to be phi inverse of UI.
This has to be 5 inches?
Yeah,
this.
that there. Okay, so we've done it, and then the phi inverse of UI would be the subset of RM. Erase the subset of RM.
This bit?
Yes. No, above. UI is a subset of the manifold.
Okay.
And then phi I, yes. Yes, that's a subset of RM. Okay. I mean, it's not a circular definition, but well, it is. It is okay in some sense, but it's not. Okay. So this map phi I now is quite literally, I'm taking some patch in Rm, which has coordinates, and then in a bijective way, assigning it to some set in M. And so I'm giving coordinates to some area of M. Okay. And now the hope is that I will want that yes, phi I inverse. And then the hope that I will want is that for all P, there exists a UI that P is contained in.
Okay.
What? Oh, that's a phi.
Yeah, well.
Okay. Because that looks like P inverse of P.
Okay, so how much of this I have to explain? Because I was like kind of following the book's way. I was like about to talk about coordinate charts, the compatibility.
So, okay. This is what you.
Okay, so I already introduced them.
Okay, and now we want our coordinate charts to be very nice, but the
my coordinate chart is this tuple, yes. By the way.
Is this correct? Yes.
So this definition is to say that if
we're not done with the definition, but yes, go ahead.
Like, this doesn't really feel a manifold.
What a manifold will be the set M with this collection of pairs. That is what a manifold is.
So the condition that every point P in M is covered by some view.
Yes.
Is that the definition that makes the set M?
We're not done yet. So the condition is that I have a set M with these pairs UI phi I, and these UI phi I satisfy some conditions. The first condition that we want is we want to be able to cover the whole thing with coordinates. If we want to cover the whole thing coordinates, then for every P, there has to be a UI that contains it. Okay, that's the first thing. The second thing that we want is we want phi I inverse U to be an open set. So that's the second condition. Write this down. Phi I inverse is an open set in Rm. Write this down on the side where you have a lot of space.
Well, I guess.
On the right side, right hand. Okay.
Wait.
So you have a lot of space here, and you will write many conditions here. So
U, no, inverse.
So phi I inverse of UI.
Phi inverse I of UI is open.
Why?
That's a phi, right? Or am I just reading this wrong?
Which?
On the left and bottom.
All of them are phi's unless it's in brackets. Yes.
That point is phi inverse P.
Yeah. So remove the P. So okay, we are switching notation. The P is the circle. So you have to choose. Is P going to be a point in your manifold, or is P going to be a point in your coordinates?
Coordinates.
Coordinates. Okay. In that case, in that case, we're good. Okay. So P gets mapped to phi I. Remove the inverse on that one.
On this one?
Yes. Okay. So P, a coordinate, gets mapped to a point 5. Actually, I'm gonna make this worse. Can you replace P here with X?
Sure.
Because I feel like P should be a coordinate in my manifold and X is a coordinate, and that makes more sense. Sorry, we're switching around, but hopefully the switching around will eventually come together as I keep saying things and keep telling you things. So now we have to remember. First of all, the phi I, UI is open. Do you agree? That's the first coordinate we're going to have. This is going to be important to have things like work out nicely and to have continuity work. Now, what's the second condition? You tell me.
The second condition to be a manifold?
Yes, we have another condition.
The condition is well, isn't that?
So we have a condition on the UIs, right?
Mm-hmm.
So now we need another condition on the phi i's.
Okay. Well, phi i's have to be bijective.
Okay.
And they also have to be continuous both inverse and the thing.
So they have to be compatible, right?
In
that sense of
okay.
So you should draw a picture of what could happen and explain. So
yeah, that was the it makes, I guess, like more sense in chronologically in the book's order, but sure.
And this is also a very chronological order. Okay. So
sure.
Draw a second picture of what could happen on this manifold.
Okay.
No,
so
draw just another picture below it, and use a bunch of use two colors. Yes.
Okay, so we can choose a region here. We can choose a region here. They slightly overlap.
And give these regions names.
Yellow and red.
Before we were using UI, so it would make sense for you to use UI and UJ. Right?
Okay, well, yes, or I can use R. For can I?
Okay, sure.
R will not get confusing at all.
This will definitely be clear later, but okay.
Okay, with
It's okay because
I'm already stealing his presentation, so it's like,
no,
I have
it's
to give him something. Okay, sure.
so it's in between like your
Okay, so what's happening here? So what is R?
R is a set that can be bijectively mapped to like one of those.
Okay, so physically, what does this mean?
It means that on R we can we know how to define coordinates on R.
Yes. So we have one way to define coordinates on R, okay? And you also have some way to define coordinates on
this one.
On Y.
Yeah, Y.
And the problem is, I have one set on which I have defined coordinates, and then I have another set on which I have defined coordinates, but maybe in a different way. Do you agree? Like I could define different patches with different kinds of coordinates. How can I think of this? I can think of it, I can have a map I can have a map of, say, like overall Toronto, but then I can separately have a map of U of T. Do you agree? And those somehow have those are different coordinate charts for the same place. Do you see that that's something that could in principle happen? Yes.
Fine.
Okay. Okay.
Say.
And so, what is the problem now?
You're asking me?
Yes, now I'm asking you.
Well, the problem is that we kind of want smoothness of the composition.
No, we didn't get to that.
Oh, no?
So, you drew a picture, maybe. You have R, which has one kind of coordinates, and you have Y, which has some other kind of coordinates. Do you agree?
Like we want in the region of using the region of using the green region, we want to be able to continuously transfer from this set of coordinates to this set of coordinates and vice versa.
So, okay, so you're still going too far ahead. Okay.
Am I?
Yes.
Okay.
So you have the red region R, which has one set of coordinates defined on it, and another region y, which has a different set of coordinates defined, right? And in principle, these regions could have overlap as drawn there. So this means on the same region, I have two different sets of coordinates defined on it. Do you agree? On the same region, I have two different sets of coordinates defined on it. Okay, and that's problematic. Because how do we know that, like, what if this doesn't play nice? What if these two different coordinates don't play nice with each other? And so then we demand that they do play nice with each other, okay? Meaning that I can do a nice coordinate transformation from one set of coordinates to another set of coordinates. Which is, okay, now that's what you now said. So what is the second condition that we now demand?
Well, the maps are this, and essentially this and this, but probably it is the same thing in some way or another, to be they are smooth.
Are smooth
In a sense.
bijections, I guess.
Well, are they not?
Well, I mean, they're already bijections.
Yeah.
Yeah.
So this is exactly what I said. You want to continuously be able to start here, and in case of overlap, describe this point, or like in case of the overlap here, you want to be able to map your coordinates for that point here to your coordinates to the same point over here in the green region, which is natural and like physical to demand from the setup, right?
Well, yes, but in what sense? So we said, okay, I could have two different coordinate systems defined on one same region. And so now I'm saying that, okay, if this works out nicely, then I should be able to go from, it shouldn't matter if I use one coordinate system or the other coordinate system to define my manifold, right? If I have some nice compatible coordinate system, it shouldn't matter which coordinate system I use. That's what we are really demanding. It shouldn't matter which coordinate system I use. Meaning that the little bits in intersection, if I was map the green region in one coordinate, I should be able to map it exactly in a nice way to the green region in the other set of coordinates. Meaning that I need to demand that if I restrict, so one thing you should kind of be careful about, you should really restrict phi inverse composed with psi. You need to restrict it to the intersection of R intersect U inverse of phi. So let me just write this so that I'm not so that this makes more sense. So I want to demand that actually, can I have a white? Okay, so I will demand that one. So I want this region to look exactly like this region for these coordinates to be the same essentially. Right? I want, if I have two different coordinate systems defined on the same place, I really want them to just be the same coordinate system, meaning that kind of this region has to be diffeomorphic to this region. Okay? So what does this mean? What does this demand of this phi map? How it should interact with this psi map? So the condition should be that if I was to start in this green region, so what is this green region? This green region over here, this is phi inverse of R intersect, this is too many colors, U, Y, okay. And so this green region, that's just psi inverse of R intersect U, do you agree? What is this? R, yeah, see, this is too many colors, but that's okay. This is my choice of using so many colors. Okay, so that's this green region, and that's this green region. Do you agree? Do you see how that's what these green regions are? Yes, just because this map is my choice. And what I want to do is I want to say, okay, if I went from here through here and to here, this is just a map from Rm to Rm. And for these kind of coordinate systems to be the same, I want this to be, either a homeomorphism or a diffeomorphism, essentially to say that, these coordinates that overlap, it's the same coordinate system up to some diffeomorphism. So I demand the second condition. So this is first, and you had kind of the this condition. You had that condition, and then you will demand that for any ui uj, right? And so, well, for any pair ui phi I uj phi j, I want that phi I composed with so I want phi I inverse composed with phi j restricted to phi j inverse of ui intersect j to be a diffeomorphism. A diffeomorphism is just a once differentiable, at least once differentiable bijective map, where the inverse is also differentiable. Okay? So do people see how this condition tells me that I want, if I have two different coordinate charts on the same region, I want them to be essentially the same coordinates up to the diffeomorphism.
Why do you have such a weak requirement? Can't you just set them to be equal? Like, what's the advantage of having this weaker requirement?
Well, the point is that if I have this requirement, that's essentially the same thing as saying that they're equal. Like what this is saying is that, oh hey, instead of just patching this region with this, I can just use the red one.
Yeah, but surely a weaker requirement has some advantage. Or else why are you using it?
Well, so if you wanted them to be equal in what sense?
Like the phi's are equal under the restriction.
Good. The point is that if they were equal, then you probably wouldn't be able to define coordinates then on a lot of things. Or you'd need a lot more patches to do that. Because, for example, think of a sphere. The way you put coordinates on a sphere is you usually put coordinates on the top half, and then you put coordinates on the bottom half. And usually the coordinates on the bottom half are kind of just exactly minus whatever the coordinates on the top half are. Do you agree? But if you can't demand them to be equal, because this one has a minus sign and this one has a plus sign. So in the kind of at the equator where the coordinates overlap, you can't demand them to be exactly equal. There has to be some minus sign between them, and if you demanded them to be exactly equal, then you would just fail to overall get a patch. Because if you roughly what you're saying is if you demanded the intersections to be exactly equal, that means that instead of just having y, I could just consider the set of r and y together and just kind of extend the coordinates to a bigger patch. And what you're saying should end up with me demanding to have a single patch which covers everything. But then that's not always possible. I can't always cover everything with one patch.
The manifold might not be in the shape of an R.
Yes.
Some other topology of it. That's why you're splitting it up and then.
The point is that a manifold is something that if you look very close locally, it looks like flat and like Rm, but maybe if you look further away, it's not. Once again, the sphere. If you look very closely on the sphere, it looks like R2. Do you agree? Like we stand on the Earth, we look around, it looks like we're on a plane. But okay, if you go to space and very far away, you realize that actually it's not a flat plane. It's like some curved surface that has interesting things going on it, and maybe not so interesting things going on. Okay, so we have this condition, this condition. So let me just write down these other conditions, and then I'll give this back to you. So we also demanded that for any point P in M, there exists a UI that contains it. So I cover the whole manifold with my coordinates, and then I wanted this, and I don't think I wanted anything else. There's also this maximal atlas stuff, but no one cares. So, right, your question was, what was a manifold? A manifold is?
This composed of this, this, and this.
Yes. So it's a set with a collection of sets and coordinate charts. And these sets and coordinate charts have to satisfy these, I think, roughly 3 conditions. Okay? So this condition, this third condition, corresponds to I just want to give everything coordinates. And this condition says that if I define coordinates on overlapping regions, I want those to be essentially the same coordinates.
Okay.
And sorry, the last thing. So diffeomorphism, right? So phi I inverse composed with phi j. That's a map from Rm to Rm. Do you agree? We defined in the very first session what it means to be a differentiable map from Rm to Rm. Remember, I defined the Jacobian and all of that, right? So it's just diffeomorphism in the sense that the Jacobian for this map from Rm to Rm exists and is nice and whatever.
Okay. So an example of what was just said would be
maybe
other board?
swap those boards or something.
I mean,
I think this is
I don't think that anything there is no longer required.
We will use it. Don't worry. It's fine.
No, it's fine.
We're having a discussion.
Should I talk about differential forms or just
No?
And like, what is it for the manifold to be smooth? And
yeah, so a manifold to be smooth is the condition that that's a diffeomorphism.
okay.
A manifold to be just continuous is a you demand that to be continuous, and that's it.
Okay. So then we will talk about an example that was mentioned already, something that is called a stereographic projection. And if we have a sphere, actually, let me do this. Let me make it roughly a very concrete sphere. Yes. So should look familiar. So what we can talk about is how to map this sphere. And like, first of all, like whether or not we can. And the answer to that is almost. But if we can map it bijectively to a flat surface, which is in that case usually a piece of paper. So could anyone please tell me why is it almost possible? Like what will cause problems if we try to map it all to a plane of infinite, plane is infinite. Yeah. So any guesses?
If you wanted to make a sphere, how would you make a sphere? Okay, yes, correct. So what did you just do?
That's a good question.
Okay, so this gesture, what did you, okay, what was this? A piece of paper, okay. Take a piece of paper and try and fold it, okay? But then you'd need to kind of glue it at the edge, at like the tip, do you agree? So suppose I gave you a sphere made out of paper. How would you turn it back into paper? You would poke a hole in it and then you would like unravel it. Okay, poking a hole in this context means I had a point, but then I removed the point. Okay. So what you're saying is, suppose we forgot about one point on the sphere, then we can probably like unravel it into a shape. Okay?
Mm-hmm. And on a plane, let's draw this plane, where I guess this is a view from above. Where do you think is that point, that problematic point that we would like to remove for us to do that? Yeah, So the point on the plane, the problematic point, is right at the center of the sphere.
It's either at the top or at the bottom.
Yeah, and this is.
That's not the one you remove. That's the one that stays.
I mean,
exact
one is removed, the other one stays.
No, I mean on the plane, like the whole center is removed eventually. No.
No.
No?
You have like a sphere.
Or-
You remove one point and then you.
Okay.
that
Oh
point
yeah, yeah,
becomes
yeah. Okay,
one.
okay. True. So if it's quite unclear, so what we do is that for one hemisphere we have enough space here. We can just like map it, like drop it down pretty much on this circle here. For the other hemisphere, we have to work around and actually extend our region a bit more to then define it like to the remaining pieces. And the way we usually do it is messed up high school trigonometry. Okay, suppose the lower hemisphere was mapped like that, and the rest has to be projected to the rest of the plane, or like the rest of the like cut rectangle on the plane, by considering a lot of things. Well, mainly the angle. If like angle in that sense and in that sense.
This is a bit unclear. Let me try and help you a little bit. Again, that's okay. So let's go back to what we were discussing originally and what we're trying to achieve, right? I'm saying, so I want to take a sphere and turn it into a manifold. Okay? So I want to take my sphere and somehow assign coordinates to it. Okay. So let me, I'll draw a sphere. Okay, I'll draw a sphere somehow. Okay, roughly, okay, something like this. Okay, I have a sphere. And what I want to do is I want to kind of use my intuition. I can probably unravel a sphere into a plane somehow by removing a point and give it coordinates that way. Okay. So the other thing is this sphere is already in R3. Do you agree? The sphere is in R3. And so in R3, I have like an R2 subspace. So I want to try and use this R2 subspace to naturally give the sphere coordinates. And there's a geometric construction called stereographic projection. Stereographic projection. And how does it work? Okay, so suppose I take a random point in the xy plane. So I take a point x, comma y, comma 0. Do you agree? Okay. Then, so up top, at the top of the sphere, I have a north pole. So this is the point 0, 0, 1. Okay? Do you agree? Okay. So actually, first of all, we didn't say what the sphere was, right? We should say that S2, the kind of two-dimensional sphere in three-dimensional space, is all x, y, z, such that what?
Such that their norm is like either
Yes.
less than or equal to 1.
No, we want the sphere, just the surface. The sphere.
Oh yeah,
I don't want the inside.
true.
So I just want x squared plus y squared plus z squared equals to 1. Okay. So what do I want? I want So I have a point here, and then I have the North Pole. I have 2 points. If I have 2 points, what should I do with 2 points always? Draw a line between them. Good. So let's draw a line between this point and this point. Okay. Do you agree? So what will this line do to the sphere? Someone else. Say what she said just now.
Intersect the sphere twice.
Twice, what are the 2 points where it intersects? where? Okay, so one's at the North Pole and one's somewhere else. Okay. So I can then say, so this point where it intersects somewhere else, this will be the point on the sphere that xy maps to. Do you agree? So I will now call this point, I will define this as my, so let's call this point, I don't know, P. And so I will define my phi of xy as something that takes this point, it draws this line, sees where the intersection is, and maps xy to this point P intersection. Okay. Do you agree? Okay. So now, what will be the coordinate of the North Pole? So what xy will give me 0, 0, 1?
Well, in that sense, no. Well, no xy will. No.
Well, what xy will be the best one to?
The zero.
You're right. So you're right. Actually, no xy will give me this point, but which point will give me the South Pole? Right. Which point will give me the South Pole in the xy plane?
Do you have to shift the plane down to xy negative 1?
No. Why?
Yeah.
I don't think I do.
I thought you have to like sit the ball on top of the plane. So sit the sphere on top of the plane instead of the sphere.
It shouldn't matter because suppose I had a point in the xy plane inside the sphere. Do you agree?
Oh, I see it now.
I can draw a straight line, and maybe the intersection will not be between here and
Okay,
here,
yes,
but
yes.
I can still continue the line, and there will be a intersection. I'm not saying that the intersection point has to be between xy and 0, 0, 1. I'm just saying that this line will intersect twice. Once at 0, 0, 1 and once somewhere else. And let this somewhere else be this map phi of xy. Okay. So which point will the South Pole correspond to? Pardon? Yes, 0, 0. So if I look at 0, 0, the line connecting 0, 0 to 0, 0, 1 will be just the vertical line. And so the other place where it intersects the sphere will be at 0, 0, minus 1. Okay? And so now, we've managed to cover this. Okay, we've managed to now do what? We've assigned an xy coordinate to every point except for one point. What is this point? So you've already said it.
Oh, that one.
The North Pole, right? And why does it make sense that I can't assign something to the North Pole? Because think about it. I'm trying to have the kind of go. I want a line going from the plane to hit the sphere and then the North Pole, right? Everything kind of below the North Pole, right, would always if I kind of have a line going down in any way, it will always intersect the sphere somewhere else. So then I would kind of have to have something that's tangent to the sphere at the top, right? For it to only go through 0, 0, 1, but then that would be parallel to xy, right? And that would kind of be a line that goes off to infinity. So this means that we can do everything except for 0, 0, 1 with this coordinate chart. Do you agree? So this means I need a second coordinate chart to kind of hit 0, 0, 1. Do you agree? So this coordinate chart doesn't hit 0, 0, 1, so I need another coordinate chart that does hit 0, 0, 1. Yes? People agree with this? And so I can do the exact same thing, but instead of drawing a line connecting 0, 0, 1, I can draw a line connecting the South Pole. Do you agree? So this would have been phi and north, and then I could define a phi as phi south, which so this is the point of intersection of a line between xy 0 and 0, 0, 1, and this would be the point of intersection of xy 0 and 0, 0, minus 1. Do you agree? And so let's write this.
My reasoning was the prepared reasoning was slightly a lot incomplete. But I was about to say that if you indeed figure out a way to map this point here and map this point here, then when you like have to go back, but by which property, like what can tell you, like when you go back and you actually have to like, and the joint points have to be put back here and here, by what criteria will you distinguish them? Like which one should go there, which one should go there? They are different points, and like they should end up like in their own spot that they were before. And if there is no way to distinguish between that, better don't bother and remove one.
Yes, exactly. So the idea is that if you kind of use this thing and then looked at 0, 0, then you would kind of have 0, 0, 1 and 0, 0, minus 1 both correspond to it. And so you need to, you want your chart to be bijective. Right? So you have a chart for everything except for one point, and then another chart for everything except for the other point.
And apart from this thing, there is a lot of stuff that you lose when you do this projection. And there is a trade-off that is represented by having different maps of the Earth. You lose relative scale in some way when you preserve an angle. That's the most common form. Like this is one of the common formats, the most common formats. And there is also that you preserve a relative angle between things by losing the scale of stuff. That's like there is a whole, I believe, I don't remember exactly the website, but there is a whole thing where you can drag a country and like check its like actual relative size to another, because like and that represents supposed like, okay, I don't know what I'm trying to say, but I think you figured.
Yes.
Why does it matter that like North Pole and South Pole aren't distinguishable? Because they're not like if you just define like the first chart as U North and the second chart as U South.
Yes.
North and South are
Yes,
Yeah, exactly.
but when you try to define both, you claim that your thing is bijective, and like the physical way of thinking about bijectivity is that like from what you started, your projection, like whatever you had before projection, point to point, every point had its own spot.
So
and like
what he's saying
okay.
is that essentially U North and U South have to exclude the other one. So he's saying that in U North, North cannot be in U North, and South cannot be in U South. That's all he's saying.
But like in the analogy, the green region would be everywhere except the North and South Pole. There's nothing that says that the red part that's not green and the yellow part that's not green have to map to each other. So why does it matter that?
Oh yeah, so that's fine. They don't have to.
So why does it matter that like they have to be distinguished? They're not like in the same chart.
I think that's not what he was saying. He was saying that they just don't have to be in the same chart, and that's it. If they were in the same chart, then you'd get something.
Question.
Yes.
When you put these things into coordinates, you're also losing, because on a sphere, every point should be like equally treated. But when you choose this coordinate system, you're picking 2 points to be unique. So you're losing some sort of symmetry. Would that matter in physics?
You're losing some sort of symmetry?
Yeah, like rotation.
Okay,
So
sure. In that case, I can introduce more coordinate charts where I do a projection from any point that I like into some perpendicular plane, and so then I could have a lot of charts, and that would not.
So I think that's why we need like the maximum number of whatever charts.
Yes. Maybe, yes.
Otherwise, like in physics, you would run into trouble because you lose some sort of symmetry while taking a coordinate.
You're right. So you're right. So this is an important idea that usually when we start doing physics and we start seeing manifolds in physics, usually in physics these coordinate charts are given to us from some kind of physical scenario, which means something. And so if I was kind of looking at the sphere from a really particular kind of physical perspective or something, then hopefully my physics would tell me exactly what the coordinate charts have to be. And once I know what the coordinate charts have to be, then I construct my manifold using these coordinate charts. Which is why I didn't want to talk about the topology, because I just wanted to give it the topology using these coordinate charts and not worry about it. Right, okay. So I think I will type up a very quick problem for this week for people to try, which is going to be essentially, figure out what this P intersection of a line has to be in X, Y, Z coordinates. So, compute this intersection. And then, so you're going to find what this map Fn is. You're going to find explicitly what this map phi S is. And then you're going to compute this, Fn inverse. And then you're going to compute Fn inverse composed with Fs and show that it is indeed diffeomorphism of R to R. And so that's just like you have to invert, like, it's not that bad. You just have to, it's only 3 components. It's not even an n-dimensional problem. It's only a 2-dimensional problem. So that shouldn't be too bad. Okay. But do people understand what a manifold is overall? Yes?
Maybe.
Okay, you just have a thing and then you put coordinates on it. Okay, did the sentence I just said make sense? Okay, you know what a manifold is. Good. That's an example of a manifold. And let's try in the last 15 or maybe 20 minutes to discuss what a tangent is.
Okay, I will erase all of this then. Shall
Yes,
I?
yes.
So, the definition suggested by Ivy on Monday of the tangent space starts with something rather not completely obvious, but something that, let me just open my notes, converges to something obvious. So, what, like very convenient, at least. Wait, where is the?
Oh, I'm sorry. I just took all the chalk for myself.
Okay. So let's look at an X that somehow, don't ask me what it is, acts on 2 distinct functions in the following way. And the way it acts should, at P. So the functions are like are evaluated at point P. So somehow this is conveniently enough for us. Should look familiar, and hopefully it is. So what does it look like based on the properties? Like, what is one possible X that satisfies this and this?
Like you've seen the second. So what's the first line telling? What is the first line? That's some linearity condition. Actually, you're right. I'm forgetting that there should also be like a multiplication by lambda, but that's fine. What's the second condition look like?
Yes.
Pardon?
Yes.
It looks like product rule. So, okay. So in some sense.
So whatever it is, derivative is an example of that, right? And we can also talk about collection of such x's that act on at P, outputting a real number, just by analogy with a derivative. Like, I reverse engineer whatever I know, like knowing stuff about derivatives, I reverse engineer to like a more general format of what X should be. Because, like,
So sorry, why are we talking about derivatives? What are we trying to do right now?
we are trying to define coordinates on the manifold still, in a way.
Not exactly. We
No?
already have coordinates on a manifold. That's fine.
Or we are trying to define coordinates for velocities.
Yes. So the question is, I have a manifold, right? So this is something that I gave coordinates. Okay? So it's something, and I have coordinates at every point. Now, when I live in Rn, I have this notion of I can go left, I can go right, I can go straight, or whatever. So I have a idea of what directions are in Rn. Do people agree with this? Yeah. So now the question is, I want to use this intuition and define what it means to have a direction on my manifold. Why is this not easy? Because initially, a manifold is just some set. It doesn't have any notion of direction whatsoever, right? So we will now try and use these coordinates to define what it means to have a direction. Okay. Now, the insight that's really important is that if I have my coordinates, then so if I have Rn, then okay, I can think of going left, right, straight, whatever. But instead, it turns out it's more useful to, instead of thinking about just directions as I can go this direction or the other direction, it's instead easier to think of I can take a derivative in this direction or another direction. You agree? So in fact, the set of possible derivatives that I could take should be the same as kind of the directions I could go. So I'll give people a moment to think about that again. If I'm in Rn, instead of thinking about directions that I could go in, it would be equivalent for me to think about the kind of derivatives that I could take at a point in various directions. Yes? People agree with this? Okay. So I should try and come up with some notion of taking a derivative on my manifold, okay, using my coordinate terms. Do you agree? And so I can hope that if I come up with something on my manifold that looks like taking a derivative, then it will somehow be isomorphic to taking it, like the amount of derivatives that I have in Rm will somehow be the same as the amount of these things that kind of look like derivatives on my manifold, and that I would then just be able to identify these two spaces using coordinates, and just think of, just have a notion of taking a derivative in some direction at every point, and just use that to talk about directions. So just instead of talking about directions, I'll just talk about taking various derivatives in various directions. Okay, and so what he wrote, so conditions 1 and 2, those are conditions of, okay, that's what a derivative vaguely looks like. The derivative is somehow linear, and the derivative has the Leibniz, the product rule. Okay? So now I'm saying, suppose I'm at a point P, and let's look at these things called X that do what? They take some infinitely differentiable function at point P and output a number. So they take in a function and that's defined at point P and output a number. And so let's look at all of X that take in a function X and output a number, that they have these two properties, that they have a product rule defined on them, and that they have a linear property. So one thing that has not yet been defined on here is what has not been defined in those three lines. So like top line, second line, third line, what has not been defined? People in the front row, what has not been defined in the third line?
TPM.
Well, no, TPM is defined using the expression on the right hand side. So that's what we're trying to define what TPM is. Yes, so CP infinity. What is CP infinity? What is CP infinity?
You're asking me?
Yes.
Okay.
Because you were the one who.
So CP infinity is a what is called equivalence class, right? No?
No.
Of okay, so basically,
Think about equivalence classes. Just say it's some function.
okay, it's a bunch of functions that you can differentiate without problems infinitely many times, that are all defined at P, and that in the region around P are also defined and are.
So not quite.
No?
Because, like, you're saying the right words, but differentiated in what sense? Differentiable in what sense?
In the sense that that's a good question. Aren't we trying to define it?
So, okay, so people, so let's stop for a second. People agree that if we knew what this was, then these x's would somehow look like something like derivatives. Agree? And hopefully then I could talk about these guys as my directions instead of talking about derivatives. But so let's see. Suppose I have my manifold, and I have some point P around. Okay? Since I have some point P around it, then okay, there should be some coordinate chart to some u, right? Okay, so I should be able to give this coordinate somehow. Okay? So now suppose I have some function f that goes from u into r. So it takes a point here and just assigns me a number. Do you agree? Can I differentiate this function straight up like this? Yes or no? Raise your hand if you think yes. Raise your hand if you think no. Higher. Higher. Why can I not differentiate it? Because we don't know how, right? How did we define derivatives, right? We defined derivatives to be something like f of x plus u is equal to f of x plus the derivative of f at x dot u plus some remainder. Okay? Why can I not write this thing for this? Why can I not write an expression like this for this function? So does this plus make sense? Does this plus make sense? Yes, because these are numbers. Does this plus make sense? No, because I have no sense of how to add numbers on my manifold. So I just can't take a derivative of a function that starts here and outputs a number. Right? Because it doesn't make, what do you mean take a derivative? What direction? But this is a manifold. So it has to have some coordinates that I can use and define differentiation that way. Okay? So what I can do is instead of looking at phi, I can look at phi f precomposed with phi. Do you agree? And now this is a function from Rm to R. Do you agree? I usually speak loud enough so it doesn't matter. Do you agree? So now this is a function I can differentiate. Right? So I have some function defined on my manifold, and I just look at how that function would look like in coordinates instead of on the manifold. And once I look at how this function looks like in coordinates, then I can differentiate it. Okay? Good. So in that case, C at point P infinity is the set of all functions f from, from say u into R, where u contains P, and f composed with phi I is differentiable, infinitely differentiable for any phi I. So I'm looking at all of the functions where if I look at how this function looks like in coordinates, I can differentiate it infinitely many times, regardless of what coordinates I choose. Okay? And so that's what I mean. This is what we mean by CP. Okay. Okay. Do you see? Hmm? Oh, P means at this point, at the point P.
So it's for all phi that this pre-image contains P.
Yes. Well, yes. So UI. Yes. So because I'm interested. I want to define directions at a particular point. So then I will look at all the derivatives at that particular point. And to do that, I have to first define like these functions, and then we'll look at how to differentiate them. Okay, so I think in the interest of time, I'll just finish this discussion quickly, and yes, that's okay. Don't worry. Okay, so let me do a quick recap. So hopefully we'll finish in 10 minutes, and it will all be very clear. Let me draw some more images. So I have my manifold. Do you agree? Okay. And this manifold has some, this manifold has some coordinates defined on it. So this is Rm. And around every point, I have some coordinate chart, which lets me assign coordinates to my points. Do you agree? So this is kind of my chart. Yeah, and so let's say this is the region where I've defined my coordinates. Do you agree? Okay. And so suppose this is the point that maps to point P equals I don't know, X or whatever. This is it. Okay. So if I'm sitting here at this point, then I have all of these directions I could go into. Okay. So I have directions at kind of point X, right? And these directions at point X should be the same as all the directional derivatives I could take. So the directions are like vectors V and Rm. All directional derivatives I can take. So everything that's all of these guys. Do you agree? So instead of thinking about all of the directions that I have at this point, let's think about all the derivatives I could take at this point. Right? And you remember I can take a derivative in a direction. Yes? Roughly. And so that's what I mean by this. Okay. What is a derivative at a point? What is a derivative at a point? It is some linear operator which does what? It takes in a derivative does what? What does a derivative do? It's a linear operator which takes in something, outputs something. What does it take in?
It takes in a point and gives you a linear approximation.
Sure, but alternatively, it can take in a function and output a linear approximation, which at a point P is a number. So if I have a scalar function, so this takes in C infinity functions from Rm to R and outputs a number. Do you agree? This is what derivatives are. There's something, they're linear operators, so linear operator that takes in a function and outputs a number. This is what a directional derivative at point P is. Do you agree? Yes? And a derivative also has a product rule. So and has product rule. Do you agree? Okay, so this is so far just in Rm. Okay? So the directions in Rm are the same as these directional derivatives. But you see that these directional derivatives are something that takes in a function, outputs a number. Okay? So if I want to define directions on my manifold, instead of thinking about directions, let's try and find something that looks like these derivatives. So then I define this thing called the tangent space at point P of my manifold. So define tangent space at point P and M to be the following set: TP M, so the tangent space of the manifold at point P, is the set X, so the set where the elements of the set are X, things that take in infinitely differentiable functions in the sense of coordinates, and output a number such that X is linear and X has Leibniz rule. So X has those two conditions, i.e. X of f plus lambda g is equal to X of f plus lambda x of g, and X of f times g, so this is all at point P, right? So is equal to g at P, X of f times the number g at P plus f at P times X of g. Okay. So given a manifold, at a point I can look at this set of things. Do you agree? And these things satisfy properties which are very similar to the properties of a derivative. Okay? Do you see? And so the argument is that there should be some isomorphism between this set and this set. So let's make a few comments straight away. So I've rewritten this over here. Let's make a few comments about all of this. So maybe I shouldn't have already started. That's okay. So the set TPM, first thing that you should notice is that this is a vector space. Do you agree? Because the things in here are linear maps. Right? I have some set of linear maps with some particular property on them. So overall, it should be a vector space. You can check that it's a vector space. It's very easy. Do you agree? That's already good, because this means that this thing we're trying to define as my set of directions at a point P is a vector space. I would expect my directions at a point P to be a vector space. Right? Very good. And now I'm saying, so what do I have? I have these local coordinates. At every point, I have these local coordinates. So it better be the case that my local coordinates over here should somehow be the same, like my directions and local coordinates over here should somehow be the same as my directions over here. Do you agree? So over here, I had what? Over here, my tangent vectors were partial x1, partial x2, so on and so forth, up to partial x m. Do you agree? Versus here, the tangent vectors, the kind of directions, were these elements of TPM. Do you agree? So there should be a way to map these onto these and these onto these. Do you agree? Okay. I will show you a map from here to here, and then I will just say that the map is invertible, and you're going to have to trust me. Okay? But it's clear that it should work out. So, what is the map? So I'm going to take a derivative in some direction v on my coordinate chart. Okay? On some coordinate chart. And I'm going to send this to the following map. It's a map that's going to take f. So I'm going to first choose choose coordinates phi. So choose a okay, so first I'm going to choose and fix my coordinates. Okay? And after I choose my coordinates, then I will have what? I will take f. I will define this map that takes a derivative in the direction of e, and maps it to something that takes in a function f and sends it to f to the derivative in the direction v of f composed with my coordinate chart evaluated at phi inverse of p. Okay. And so the claim is that this is a map from directions in Rm into TPM. Okay. So what did I do? I essentially said, okay, let's take my derivative and talk about and introduce this linear operator of differentiating functions in coordinates with respect to the same derivative. Okay? So remember, TPM was this set of linear maps which take in a function, output a number, and has a Leibniz rule. Okay? And I'm saying that that should be like my directions in Rm. Sorry, that should be like my directions on the manifold. And so if it's like my directions on a manifold, it should be the same as my directions in my coordinates. And so here I define a map that takes the directions in the coordinates and gives me something in what I define to be the tensor space. Okay? And it's the same as just taking a derivative in coordinates in the direction v. Okay? So what I'm saying is, if I have some direction v, I can take a derivative in this direction. Okay? And so taking a derivative in this direction on here should be the same as just taking a derivative in coordinates on here. Okay, and so this will just be, taking a derivative with respect to v, but then I precompose this with phi. Whatever I do. Okay. So do people get this idea that I had a notion of direction on Rm, and I realized that that's the same thing as just looking at all the derivatives that I could take in some direction. Yes? Does that make sense? Okay. And then I define this thing TPM, which I've defined this thing TPM on my manifold, which looks very much like taking a derivative on my manifold. Okay? And then I just realized that actually taking a derivative in my coordinates should be the same as these taking derivatives in my manifold, and so those two should be the same. And so I should define my directions on my manifold as taking derivatives in coordinates. Okay. So this roughly makes sense. Hopefully, that's fine. It's 8:40 p.m. so no one's understanding anything. That's fine. And so now I will make like a huge leap because we're running out of time. But now what I will do is I will define this thing called Tm, which is going to be a disjoint sum over every point p in the manifold of TPM. So TPM was some directions at point p of my manifold. Do you agree? So at every point on my manifold, I have some directions, and I call that TPM. That part makes sense. Forget about maybe what TPM is. Just think of TPM as like directions at point P on my manifold. Okay, and then I can just take a union over all the points in my manifold. Right. So at every point, so I have my manifold, at every point P, I look at the directions at point P. Okay, and so I union over every single point. So I just kind of look at the total set of all of these vector spaces at every point. Okay? And then what I can do is I can give this set coordinates and turn this into a manifold. And the coordinates for this are going to be very simple. So let's call this map some, I don't know, capital X. And so I will give this coordinates in the following way. That, let's define coordinates psi I, where psi I of x comma v is going to output me where do I specify the point? So this is x at p. It's going to give me x of v at, well, x of partial v at point phi I x. Okay. And so therefore, and Tm, which we will call the tangent bundle, is a manifold. Okay. So what I did, roughly, I'll give a moment, I'll say concluding remarks, and we'll stop. What I did is, I'll give you another moment. If you have to go, please go. Disjoint sum means that at every point I have some directions, but then the directions at one point could be different from directions at another point, and they're unrelated. Like roughly speaking, on a sphere, if I have a sphere and I'm here, the directions I could travel in are very different from the directions that I could travel in at this point here. And so I have to take a disjoint sum so that I really specify that the directions I could go in at every point are unrelated to each other.
So you're just manually making them.
Yes. And I mean, they are disjoint in principle.
Yeah.
Okay. So let me go back. So we started off with a manifold, right? A manifold was some set, and I could put coordinates on this set. Do you agree? Then I said, okay, I can use these coordinates, and I can look at a specific point, and kind of look at the region around this point in coordinates. Do you agree? In coordinates, I have a well-defined notion of direction, which is in fact the same. This notion of direction is the same as taking a derivative in that direction. Okay. So then I define this thing called TPM, which is essentially taking derivatives in various directions. Okay, so it's some notion of derivatives on my manifold. Okay, and I said that let's fix a point P and look at all the derivatives I can take at point P on my manifold, and call that my tangent space to the manifold. Okay? So the tangent space to the manifold is all the derivatives I can take at that point in the manifold. Do you agree? And then I said, okay, now that I have this notion of derivatives at every point on the manifold, right? So I have like this tangent space, this set of vectors which are tangent to that point P. I can then look at every point P. At every point P, I have this tangent space, okay? And then I can just create this huge set of all the tangent spaces at every point in my manifold. So I take every point, at every point I have a tangent space, and so I can look at the total set of all the tangent spaces at every point in my manifold, okay? And that will be the tangent bundle. So that's just, I took a manifold, at every point I attached a tangent space to it, okay? And that's called the tangent bundle. And it turns out that this tangent bundle is also a manifold where the coordinates are taken, where the coordinate charts are taken from the coordinate charts that I had on my original manifold. Okay. All right.
So this
So, yes.
this manifold is now in like locally homomorphic to R2n.
Correct. So this is a where is it? So Tm. This is now a 2m dimensional manifold because to specify a tangent vector at a point, I have to first specify to you where the point is, and then I have to specify what the tangent vector at that point is, right? And I need m coordinates to specify where the point is, and then I need another m coordinates to specify the direction. And that's exactly what this is saying. I defined a coordinate chart where the first m numbers tell you the point I'm at, and the second m numbers tell you which direction I'm going starting at that point. Okay? So maybe I'll have like some additional review session at some point with this, because maybe this was not all clear. And I'll try and come up with an exercise for computing these things.
Yeah, I'm just like evaluating everything in my head.
Yes. So xp takes in a derivative and outputs a derivative. So given a choice of coordinate chart, I can define these xp's, which take in a derivative and output for me a something in TPM. So something in TPM is something that takes in a function and outputs a number. Right? This is a number. But roughly, this operation is just taking a derivative of f in coordinate chart phi, all in the direction v.
Yes.
Right? So I take a direction and map it to the operation of taking a derivative of functions in direction v in coordinates. And that's all I did. So all I'm telling you is that directions are kind of the same as taking derivatives. So let's define my directions to be my derivatives that are available to me in coordinates. That's all I said. That's maybe not immediately clear. I'll try and write up 2 exercises. One is going to be the annoying sphere one, and one is going to be something simple with a circle where you get to compute some of these things. Okay? All right. Sorry if this was. I thought this is exactly what I was saying on Monday. Maybe I didn't make it clear. That's okay. But does it make more sense now than before? Okay, so like I do not mean for these reading groups to be where people come in and they. Okay, so YouTube people, I'm done. There's no one on YouTube.